Hello everyone. Now we're going to learn about tangents. So here's our first theorem. It says if a line is tangent to a circle, so that means it touches it at exactly one point, then the line is perpendicular to the radius drawn to the point of tangency. Okay? So if I draw a radius out here and I draw another tangent line there, that tangent line is perpendicular. So here's a corollary. Tangents to a circle from a point are congruent. So let's draw a point out here. And from this point, I'm going to draw two tangents. And we're going to prove that they're congruent to each other. From there to there will be congruent from there to there. All right. So what we can do is, if this is the center of the circle, and if I draw a radius out there and a radius down there, then from that theorem we just learned, these are perpendicular. And if I draw that line right there connecting the center to this point out here, well, since these are both radii, they're congruent. And since the two triangles share this hypotenuse right there, it's congruent by reflexive property. So we have hypotenuse leg, which means by CPCTC, corresponding parts of congruent triangles are congruent. These pieces are also congruent. Okay, and then the last theorem we're going to talk about is just the converse of the first one. It says if a line in the plane of a circle is perpendicular, then it must also be congruent. I'm sorry, and it must also be tangent, not congruent. Okay? All right, so here's just some definitions. You can have external tangent lines to two circles, and they look like this. There's one that way. There's one that way. Now, how do we know they're external tangents? Because if I drew an imaginary segment between the two centers, neither of those tangents would cross that imaginary segment, right? Okay, now here's an internal tangent. It's going to go, well, I'm going to miss it, aren't I? Hang on a minute. It's going to go like this. Okay, now how do I know that's an internal tangent? Because once again, if I draw an imaginary segment between the centers of the two circles, that tangent does cross that segment, so it's called an internal tangent. Now circles can be tangent to each other. So these two circles are externally tangent because this circle is outside this one. And these two circles are internally tangent because this is tangent to the bigger one and it's inside the bigger one. And notice that they're both tangent to a line if we drew a line like that, okay? All right, let's do some examples. So what if you had this picture right here and you were told that OT is 6 and JT is 10, then how much is JO? Well, by the theorem we just learned, that's a right angle there because tangents are perpendicular to radii, which means we have a right triangle, which means we can use the Pythagorean theorem. So we can say that JO squared is 6 squared plus 10 squared. So JO squared is 36 plus 100, which is 136. So JO is the square root of 136. Now I can take a 4 out of that. That's 4 times 34, which means that this ends up being 2 root 34. Okay, last example. R, S, and TU are common internal tangents to the circle. So if RZ is 4.7 and ZU is 7.3, find RS. RS is this whole thing right there. And TU, that's that whole thing right there. Okay, well, we learned that segments tangent to a circle from a point are congruent. So if this piece is 4.7, then this piece is also 4.7. If this piece here is 7.3, then this piece here is also 7.3. So now we can say that RS is 4.7 plus 7.3, which is 12.